Welcome to next lecture. In the previous lecture, we just had an introduction to start with the three-phase rectifier circuits. The main motivation in starting three-phase rectifiers is when the number of pulses in the converter operation is increased, output voltage is more nearer to DC waveform and some of the harmonics in source current will be eliminated. Due to that, size of source filter as well as load filter will reduces. With that motivation, we started three-phase rectifier circuits. So, in three-phase rectifier circuits, what is the basic concept? When we are considering phase voltages as reference, at omega t is equal to 30, 150 and 270 degree, any two phase voltages will cross in the positive half side. So these 3 points were named as positive phase crossover points. In the negative side, 90 degree, 210 degree and 330 degree, at these points any two phase voltages crosses in the negative side, hence these points were named as negative phase crossover points. With that concept, in the previous lecture we discussed common cathode as well as common anode configuration circuits. Okay, so in common cathode configuration, what is the basic concept? The device which is connected to higher positive potential will forward bias. Now the next circuit is three-phase half-wave phase controlled rectifier circuit. What is the basic concept here? Earlier diodes were replaced here with the thyristors T1, T3 and T5. Now before going into this circuit, for example, if you look into single phase circuit, there is a single phase AC source and we have one thyristor and load is a resistor. Okay, load is a resistor. Now in this particular circuit, what is the basic concept? If you look into source voltage waveform, firing angle was measured from positive zero crossing of source voltage. Firing angle was measured from positive zero crossing of source voltage. For example, in this circuit, if we give alpha is equal to 0 degree, then this SCR will start conduction from omega t is equal to 0 itself. There is no delay. Suppose if we give alpha is equal to 15 degree, then SCR will start conduction from this positive zero crossing of the source voltage, firing angle is measured. From that instant, after 15 degree, device will start conduction. And hence firing angle is also named as delay angle, or you can also call it as firing delay angle. But now coming to three-phase situation, three-phase rectifier circuits, if you see here, T1 device is not ready to start from 0 degree. T1 device is ready to start from this positive zero crossing of source voltage. Okay, so T1 is ready to start conduction from omega t is equal to 30 degree. Similarly, T3 is ready to start from omega t is equal to 150 degree. T5 is ready to start conducting from omega t is equal to 270 degree. Now, if we give alpha is equal to 0 degree here, remember carefully, if I say that in the rectifiers chapter alpha is equal to 0 or alpha is equal to 15 degree, the same firing angle is given to, same in the sense, same alpha will be applicable for these three devices. Okay, there will be three gate drive circuits. So those three gate drive circuits from their respective starting points with a delay of either 0 degree or 15 degree, firing angles will be given. Okay, so alpha is equal to 0 or alpha is equal to 15 means T1, T3, T5 for the three devices, or next class we will see that bridge rectifier, there will be 6 devices. Means point is, whatever firing angle we are talking about in three-phase rectifiers circuits, same firing angle is applicable for all the devices. Same firing angle means there will be individual gate drive circuits, but all of the gate drive circuits will produce firing angles exactly either 15 or 30 degree. It depends on the application. Okay, and don't give me counter for T1 15 degree, T3 30 degree. What will happen, sir? That will not take place in the rectifier chapter. Such a scenario is there in cycloconverters, not in the rectifiers chapter. Okay, now for example, first let us draw the conduction sequence diagram by considering alpha is equal to 0 degree. If alpha is equal to 0 degree, conduction sequence diagram should be same as that of diode. Okay, so let us see whether we will get it or not. If alpha is equal to 0, we can say that T1 device will conduct from its respect to phase crossover point. What is that? 30 degree. Therefore, T1 will conduct from 30 degree. Next, T3 will start conduction from its respect to phase crossover point, that is 150 degree. Okay, T3 conduction will start from 150 degree. T5 conduction will start from 270 degree. Okay, T5 conduction will start from 270 degree. Next cycle, T1 conduction will start from 390 degree. So 390 is the same as that of 30. Therefore, 360 to 390, I can write it as 0 to 30. That is T5 device. Now, from the previous diode circuit, what we discussed, if T1, earlier it was a D1. So, when T1 is on, X can be connected to A. Under that condition, we can say that output voltage is equal to VAO. Okay, next. When T3 is on, X can be connected to B. In that condition, output voltage is equal to VBO. Similarly, when T5 is on, X will be connected to C, hence output voltage will be equal to VCO. 0 to 30 also output voltage will be VCO. Okay. So once you had this conduction sequence diagram, now the next step is look into source voltage, the respective intervals, and then draw the corresponding waveform shape. Okay, and the corresponding waveform shape. So 30 to 150, 30 to 150. If you draw blue color sinusoidal, it looks like this. 30 to 150, V0 is same as that of VAO, right? 150 to 270, output voltage will be same as that of VBO. So that is a red color sinusoidal. Okay. 270 to 390, output voltage is the same as that of black sinusoidal, and 0 to 30 also it is same as that of VCO, hence it is a black sinusoidal. Okay, so this is what output voltage waveform for alpha is equal to 0 degree. Now if you compare this conduction sequence diagram and V0 waveform with respect to diode circuit in the previous lecture, both are same. Alpha is equal to 0 means SCR circuit will just behave like a diode circuit. So going forward step by step, when you are drawing the waveform, what you can do, my sincere suggestion is you write down some numbers to this particular waveform. Okay, at this moment let us call waveform number 1, because at a one stretch I cannot draw all the waveforms here. So if I erase any particular waveform, later on I will refer with the numbers. Okay, for that you just use waveforms, immediately you just write down a number, right? This is about alpha is equal to 0 degree. Now, if you give some firing angle, okay, let us give alpha is equal to, for example, 15 degree. Then we will see what is the modification in these waveforms. What is the modification in these waveforms? For example, I am giving here alpha is equal to 15 degree. Alpha is equal to 15 degree. Follow carefully step by step. So when alpha is equal to 0, that is a 30 degree, always take this conduction sequence diagram as a reference. Even if I erase these waveforms later, I will not rub this alpha 0 conduction sequence diagram. So from this point, if alpha is equal to 15 degree, now delay this conduction by 15 degree. Then what will happen? T1 device will start conduction from omega t is equal to 45 degree. Okay, so write down T1 here. Now T3 will start conduction from 165. So what is the basic concept here? From their respective phase crossover points, each device conduction will be delayed by whatever firing angle we are providing. At this stage, we are giving firing angle of 15 degree. Hence, each device conduction sequence is delayed by 15 degree. Or in simple words, what I can say, if I stand in this direction, previous conduction sequence diagram is just right shifted by 15 degree. Like that also you can see. So T3 will start conduction from 165 degree. Now at this stage you might get the concept. T5 will start conduction from 285 degree. Okay, so that next cycle T1 will start from 405. I'm sorry, T1. So T1 will start from 405 degree. So 360 to 405 is same as that of 0 to 45. Okay, so this is what conduction sequence diagram. What is the next step? Once you have these devices conduction sequence, next step is write down these voltages. When T5 is on, VCO, T1 is on, VAO, T3 is on, VBO, T5 is on again VCO. That is the second step. What is the third step? You should draw the corresponding waveform shapes. Okay, you should draw the corresponding waveform shapes. Now what you can do here, look into VAO waveform from 45 to 165 and 165 to 285. You should look into red color sinusoidal. Now follow carefully here. I am just taking one horizontal line for reference. 0 to 45. Everyone look at the source voltage. See, follow carefully. This instant is a 30 degree instant. This instant is a 60 degree instant. 45 means in the middle. Okay, 45 means in the middle. Now if you see in the middle, black sinusoidal up to 45, you draw black sinusoidal. Up to 45, draw black sinusoidal. Now at 45, I can notice that blue sinusoidal is above this black one. Therefore, I will have a little jump over this. Okay, next VAO you need to draw. So VAO has a positive peak at 90 degree. So 45 to 90, it will increase us to positive peak. After that it comes down. After then it comes down. Okay. Now one more point. At 165 degree, suppose if you draw this waveform exactly, if you put one scale horizontally, you will notice that VCO value at 45 degree is same as that of VAO value at 165. That is why here I took one horizontal reference. Now with this explanation, if you draw VAO waveform, it will be like this. Okay. At 90 degree, this waveform will reach us to positive peak. In the similar way, 165 to 285. Okay. So at 165, VBO red color sinusoidal is a little bit above blue sinusoidal. Now VBO will have a positive peak at 210 degree. Okay, 210 degree. Next, after 210 it will come down. Therefore, VBO value at 285 is same as that of VAO value at 165. Therefore, we will have VBO waveform something like this. VBO waveform something like this. Okay, next. VCO is a black sinusoidal. So VCO will also have the same explanation as of previous pulses. Okay, so this is what output voltage waveform for alpha is equal to 15 degree. Okay, so what I can say here, I will consider this waveform number 2. Okay. Now, after this, I will erase these waveforms. Now, for average and RMS values calculations, you need to define the pulse limits. Okay. So, follow carefully. How can I write down this pulse limit? How can I write down this pulse limit? Now, tell me, what is the reason for T1 to start from 45 degree? T1 is started from 45 because alpha is added to 30 degree. 30 is a reference for us. Therefore, we can express this point as pi by 6 plus alpha. Okay, pi by 6 plus alpha. Now, this point we can write it as, see, T3 is started from 165 because alpha is added to T3 reference. What is T3 reference? 150. Therefore, this point can be expressed as 5 pi by 6 plus alpha. Okay, 5 pi by 6 plus alpha. Therefore, if you need to find average or RMS values for this particular waveform, you have to take the limits for integration as integral from pi by 6 plus alpha to 5 pi by 6 plus alpha. The waveform is blue color sinusoidal. Okay, what is the equation for blue color sinusoidal? VAO. What is the equation for VAO? VMP sin omega t. Okay, just remember that. Next, one more important point, that is now, for example, if we consider load as a resistor, we know that output current waveform also have the same waveform shape as of V0 waveform. Therefore, same waveform shape in 3 phase, it is very laborious. So we will not repeat similar and same waveforms. Okay, so we can understand that I0 waveform will be just similar to these 2 waveforms. Okay, so when you are observing these 2 waveforms, I can say that these, suppose if I draw I0 waveform, will also have same waveform shape. Now follow carefully. These 2 waveforms are above x-axis, right? These 2 waveforms are above x-axis. What do you mean by that? Current waveform is also above x-axis. That means in this particular case, if the load is resistive for alpha 0 and 15 degree, even though load is resistive, what is the nature of conduction? The nature of conduction is continuous conduction. Again, one more point, it is not continuous conduction always. Okay, at this stage it is a continuous conduction. If I increase alpha little bit, what will happen? Now observe carefully. For example, if I take alpha 30 degree, in that we will take up that next. In that case, T1 will start conduction from 60 degree. In that case, VCO will extend up to 60 and it will touch x-axis. Therefore, if alpha is 30 onwards, conduction behavior is different. So what we can say at this moment for resistive load, okay, let us better to write down these conclusions. Suppose if we have load as resistive load, right? When alpha is less than 30 degree, when alpha is less than 30 degree, what is the conclusion? V0 and I0 waveforms are as shown in waveform numbers 1 and 2. Write down these points clearly. Waveform numbers 1 and 2. Okay. Next, what is the nature of the conduction? Continuous conduction. Okay. What is the nature of the conduction? That is a continuous conduction. This is when alpha is less than 30 degree for resistive load. Suppose if alpha is equal to 30 degree, then what is the scenario? Let us see that. Now, let us look into alpha is equal to 30 degree conduction sequence diagram. Okay. So, when alpha is equal to 30, T1 will start from 60 degree. Okay. T1 will start from 60 degree. T3 will start from 180 degree. T3 will start from 180 degree. T5 will start from 300. T5 will start from 300. Next, T1 will start from 420. Okay. T1 will start from 420. So 360 to 420 is the same as that of 0 to 60. 360 to 420 is same as that of 0 to 60. Okay. Next. So once we got this conduction sequence diagram, what is the next step? That is, now write down the voltages. When T5 is on, voltage is VCO. When T1 is on, voltage is VAO. When T3 is on, this is VBO. Again when T5 is on, that is VCO. Okay. So that is the next step. Now, after writing this conduction sequence diagram, then what is the next step? We need to draw output voltage waveform. We need to draw output voltage waveform. So now in this particular condition, a slight difference. Follow the difference carefully. From 0 to 60 degree, look into source voltage VCO waveform. Okay. VCO waveform is a black sinusoidal. That black sinusoidal will touch x-axis at omega t is equal to 60 degree. Okay. Next, from 60 degree to 180, we need to draw VAO. What is VAO? Blue sinusoidal. Okay. So from 60 to 60 means VAO is above x-axis. At 90, VAO will have positive peak. After then, it will come down and it will touch x-axis at omega t is equal to 180 degree. Therefore, VAO waveform, the pulse shape is like this. VAO waveform, the pulse shape is like this. Next, from 180 to 300, 180 to 300, VBO, that is red color sinusoidal. Okay, red color sinusoidal will be like this. VBO will touch x-axis at omega t is equal to 300 degree. Okay. Next, from 300 to 420 degree, output voltage is VCO. Therefore, VCO is a black sinusoidal. It looks like that. Now, for our reference, what I can do, let me take this waveform number 3. Let us take that is waveform number 3. Now, what is the important point to understand from this waveform? What is the important point here? That is, output voltage waveform just touches x-axis. If I draw output current for a resistive load, exactly output current waveform is also same as this. So what do you mean by that? At omega t is equal to 180 degree, we can say that conduction is just continuous. Let us write down that point here. When alpha is equal to 30 degree, the first point is V0 and I0 waveforms are as shown in V0 and I0 waveforms are as shown in waveform number 3. Okay, waveform number 3 we plotted only as V0 waveform. However, I0 will also have the same waveform shape when the load is a resistive nature. What is the conduction behavior in this case? This particular waveform will be considered as boundary between continuous and discontinuous. Okay, alpha is equal to 30 degree will be treated as boundary between continuous and discontinuous conduction. Why we use the word discontinuous conduction, that you will understand next if you take alpha greater than 30 degree. Now let us look into conduction sequence diagram for alpha is equal to 60 degree. If alpha is 60 degree, T1 conduction will be delayed by 60 degree. Therefore, T1 will start from 90 degree. Okay, T1 will start from 90. But observe carefully here, at 60 degree, okay, this is a 60 degree. Before that, T5 is in conduction, but there is a slight difference. Follow carefully here. After 60 degree, VCO, the black sinusoidal, is going to be negative. What do you mean by that? In case of resistive load, I0 waveform will also follows this VCO waveform. But after 60 degree, as VCO is going to be negative, look into the circuit diagram once. Where I0 is going to be negative means current will flow in this direction. But through T5, tell me, is it possible for current to flow from cathode to anode of T5? No. Then what will happen? What is our statement? SCRs will conduct in two situations. One is, if at all it has zero crossing, it will turn off. Otherwise, devices will turn off only when the next devices starts the conduction. So in this particular case, T5 current will have zero crossing at omega t is equal to 60 degree, because current waveform will simply follows the voltage waveform in case of resistive load. Therefore, T5 will stop the conduction at 60 degree, and hence 0 to 60 degree we will have output voltage of VCO. But 60 to 90, no devices will be in conduction. Therefore, in this interval, there is a discontinuity. Okay, that is why we told discontinuous conduction word. If alpha is greater than 30 degree, 60 will come under greater than 30. So if alpha is greater than 30 degree in resistive load, there is a possibility for discontinuous conduction. Now from 90 to, observe carefully here, 180, 90 to 180, T1 will be in conduction, so that output voltage is VAO. But when alpha is a 60 degree, T3 conduction will be delayed by 60, that means from 150 delayed by 60 means T3 will start from 210, therefore T3 will start conduction from 210. But T1 is turned off at pi itself. What is the reason for that? Because current waveform will have a zero crossing at pi, because I0 will be followed by VAO. Okay, therefore 180 to 210 there is a discontinuity. 180 to 210 there will be a discontinuity. Next, 210 to this instant is 300. Okay, 300. Which device is in conduction? That is T3 device. Okay, that is a T3 device. But when T5 will start conduction, that is from 330. That is from 330. Therefore, 300 to 330 there is a discontinuous interval. After 330, T5 will start conduction. Now when T5 will stop conduction, that is at 420 degree, and 420 to 450 there is a discontinuity. Okay, so in this discontinuity no devices will be in conduction. T1 will start after 450. Okay, now when T3 is in conduction, output voltage is VBO. When T5 is in conduction, output voltage is VCO. Okay, so this is about conduction sequence diagram for alpha is equal to 60 degree. Now if we draw output voltage waveform by looking into the respective intervals, we will get waveform like this. Okay, so 0 to 60 degree, 0 to 60 degree, output voltage is VCO. 0 to 60 degree, output voltage is VCO, that is a black sinusoidal. 90 to 180, 90 to 180. At 90 degree, VAO has positive peak, and 180 degree, VAO will reaches to 0. That is how VAO pulse waveform shape will be like this. Okay. Next, now during discontinuity, output voltage is 0 because load is not having any EMF term, only resistive load. Next, 180 to 210, it is a discontinuous interval. 210 to 300, output voltage will be followed by VBO. That is how the waveform shape is. Next, 300 to 330, there is a discontinuity. 330 to 420, output voltage is followed by VCO. Output voltage is followed by VCO. That is how output voltage waveform. Now let us give a number 4 for this waveform. Okay, number 4 for this waveform. Now if you look into limits for this waveform, tell me what instant this T1 is started, that is at 90. Now what is the reason for it to be started at 90? Because alpha is added to its reference. What is the reference? Pi by 6 plus alpha. Pi by 6 plus alpha. Okay. Now T1 stops the conduction at 180 degree. One important point to understand. For example, if I give alpha 90 degree, T1 will start from 120, but it will stop at 180. If I give alpha 120, T1 will start from 150, but it will stop at 180. So point to understand here, if alpha is beyond 30 degree, if alpha is beyond 30 degree, for 60 started at 90 but stops at 180. For 90 started at 120 but stops at 180. For 120 started at 150 but stops at 180. If you increase alpha up to 150, there is no conduction. Therefore, in this particular circuit, the maximum limit on alpha is 150 degree. You cannot increase alpha beyond 150 degree. But if you observe carefully in this sequence of firing angles, what is important observation? The upper limit is pi only. Okay, upper limit, waveform cannot move beyond pi. Therefore, this particular limit can be simply written as pi. Can be simply written as a pi. So lower limit is pi by 6 plus alpha, upper limit is a pi. Okay. Now let us use these conclusions here. When alpha is greater than 30 degree, when alpha is greater than 30 degree, then V0 and I0 waveform, V0 and I0 waveforms are as shown in waveform number 4. Okay, waveform number 4. Next, this particular condition is referred as discontinuous conduction. Okay, this particular condition is referred as a discontinuous conduction. Discontinuous conduction. Therefore, what all the waveforms we discussed till now, they are considered for resistive load. They are considered for resistive load. Now, let us look into current stiff load. Let us look into current stiff load. What do you mean by that? Output current is equal to constant. Okay, output current is equal to constant, especially in case of inductive load. Now, if you look into waveforms, what all the waveforms we have plotted till now, up to 30 degree. Okay, up to 30 degree. Waveform number 1, 2 and 3 are applicable. Okay, waveform number 1, 2 and 3 are applicable. But when alpha is greater than 30 degree, in case of current stiff load, this type of discontinuity will not come into picture. So waveform number 4 is different for current stiff load. What is that? We will see it now. Now we are considering current stiff load if alpha is equal to 60 degree. If alpha is equal to 60 degree. In this particular case, T1 will start conduction from 90 degree. Now, in our previous situation, we told that T5 will stop whenever this waveform entered in the negative side. But in case of current stiff load, load current is constant. Therefore, T5 will stop the conduction only when next device, that is T1, is a started conduction. Hence, in current stiff load, T5 will continue the conduction up to 90 degree. Okay, up to 90 degree. Next, T3 will start the conduction at 210 degree. T3 will start the conduction at 210 degree. And T1 will continue up to T3 starts. Okay. Therefore, what is output voltage in this interval? That is VAO. Next, T5 will start conduction from 330 degree. Okay, T5 will start conduction from 330. Alright, so this is a 330. So up to 330, that means up to T5 starts the conduction, T3 will maintain the conduction state. Therefore, when T3 is in conduction, output voltage is equal to VBO. Now, T5 will start at 330 and T5 will stop only when T1 is started, that is at 450. Okay, that is at 450. This is how the conduction sequence diagram for alpha is equal to 60 degree in case of current stiff load. Now let us draw what is output voltage waveform. What is output voltage waveform for this particular condition? Okay, so here when T1 is in conduction, output voltage is followed by VAO. When T3 is in conduction, V0 is followed by VBO. When T5 is in conduction, V0 is followed by VCO. Follow carefully here. 0 to 90 degree. If you draw VCO waveform shape, VCO is positive from 0 to 60 and 60 to 90 VCO is a negative. Therefore, VCO waveform is something like this. VCO waveform is something like this. At 90 degree, VAO has positive peak. At 90 degree, VAO has positive peak. At 180 degree, VAO will reach 0. Therefore, 90 to 210, if you draw VAO waveform, the waveform shape is like this. The only thing is, you should understand sinusoidal waveform very clearly. From what angle to what angle, what is the waveform shape of sinusoidal, nothing else in power electronics. Okay, if you are very comfortable in drawing sinusoidal waveform between different intervals, power electronics is done. 210 to 330 degree. 210 to 330 degree. VBO, red color sinusoidal, will be like this. VBO has 0 crossing at 300. VBO has 0 crossing at 300. 330 to 450 VCO waveform is like this. This VCO has 0 crossing at 420. VCO has 0 crossing at 420. This is how output voltage waveform for current stiff load for alpha is equal to 60 degree. Let us call this waveform number 5. Okay, that waveform number 5. Now, how can you define the limits? How can you define the limits? T1 started from 90 degree, right? Why? Because alpha is added to T1 reference. What is T1 reference? That is pi by 6. Therefore, this point can be expressed as pi by 6 plus alpha. 210 is because T3 is started at 210, that is because alpha is added to 150. Therefore, here we can write down limits as 5 pi by 6 plus alpha. Okay, so for this particular current stiff load, what are the waveforms applicable? Okay, what are the waveforms applicable? You tell me. Waveform number 1 is for alpha 0, waveform number 2 is for alpha 15, waveform number 3 is for alpha 30, waveform number 5 is for alpha 60 degree. Now if you look into waveform number 2 and 5, you will notice that whether alpha is less than 30 or greater than 30, waveform limits are same. Okay, waveform limits are same. Now let us write down these conclusions here. For current stiff load, for any alpha, okay, for any alpha, I0 is constant. Okay, I will draw in the next waveform. At this moment I have not yet drawn output current waveform. I naught is a constant. Conduction behavior is continuous conduction. Conduction behavior is a continuous conduction. Okay. What are the waveform numbers are applicable? V naught is as shown in waveform numbers 1, 2, 3 and 5. Okay. 1 and 2 are for alpha less than 30. 3 is for alpha is equal to 30. 5 is for alpha greater than 30 degree. Now, let us take another situation. We are at the stage of current stiff load. For this current stiff load, just look into the circuit diagram. Assume I placed a freewheeling diode across this load, inductive load. Okay. Assume there is a freewheeling diode across inductive load. When there is a freewheeling diode across inductive load, what will be the modifications? Again, you just go through your waveforms. For alpha is equal to 0, waveform number 1 is applicable. For alpha is equal to 15, waveform number 2 is applicable, right? For alpha is equal to 30 degree, waveform number 3 is applicable. Now, for alpha is equal to 60 degree, okay? Before going into the V0 waveform, let us have one discussion. Current stiff load, alpha 60 degree, we have got this waveform, right? Now just imagine if we place a freewheeling diode across inductive load, then what is its property? I am modifying this waveform, you need to redraw this one. Whenever output voltage waveform is going to be negative side, then what will happen? Freewheeling diode will be in conduction. Okay, therefore output voltage negative portion will be removed. Of course, you may feel that this waveform is just similar to waveform number 4, true, but what is the difference between waveform number 4 and I am going to give this number for 6, okay. So what is the difference between waveform number 4 and 6? That is, in waveform number 4, 60 to 90 degree there was a discontinuity, but now 60 to 90 here there is a freewheeling action. Here also output voltage is 0, but this output voltage is 0 because of freewheeling action. Previous case, waveform number 4, output voltage was 0 because of discontinuity interval. Okay, next. In this case, 180 to 210 degree, output voltage is 0. That is due to freewheeling action. Okay, so in this interval, FD will be in conduction. In the similar way, 300 to 330 freewheeling action. Again output voltage is 0. Okay, here freewheeling diode will be in conduction, and here also this particular interval freewheeling action, FD will be in conduction. Okay, FD will be in conduction. Now, how can you write down the limits? How can you write down the limits? These limits are just similar to waveform number 4 only. Okay, so what are those limits? Pi by 6 plus alpha to upper limit is pi. Okay, upper limit is pi. So this is a output voltage waveform. Now after this, I can draw output current. This particular output current is applicable for both current stiff load and the next category, current stiff load with freewheeling diode. Current stiff load with the freewheeling diode. Okay, so this is a output current waveform, that is I naught. Output current waveform, that is a I naught. Okay. Now let us write down these conclusions. Now let us write down the conclusions. Now look here, previous one, I naught is a constant. I can say that waveform number is a 7, where waveform number 7 is this output current. I just referred this with a waveform number 7. Now let us write down the conclusions for current stiff load current stiff load with freewheeling diode across it. Okay, current stiff load with freewheeling diode across it. Now here, when alpha is less than or equal to 30 degree, when alpha is less than or equal to 30 degree, V naught waveform is as shown in waveform number. Can you tell me what are the waveform numbers? 1, 2 and 3, right? Waveform numbers 1, 2 and 3. And I naught waveform is as shown in waveform number 7, because load current is a constant. Next, another important conclusion is there is no freewheeling action. Okay, there is no freewheeling action. Up to 30 degree, V naught has no freewheeling action. Next, when alpha is greater than 30 degree, when alpha is greater than 30 degree, in that case V naught waveform is as shown in waveform number 6. Okay, V naught waveform is as shown in waveform number 6. Next, I naught waveform is as shown in waveform number 7. Waveform number 7. Now in this particular case, there is a freewheeling action. There is a freewheeling action, right? So these are the waveform discussions for 3-phase half wave phase controlled rectifier. Next, one more important point, that is, in case of current stiff load, in case of current stiff load with freewheeling diode, current stiff load with freewheeling diode, let us generalize what is the freewheeling duration. Freewheeling duration is equal to 0 when alpha is less than 30 degree, less than or equal to 30 degree. Now, for example, if alpha is greater than 30 degree, look here. So, when alpha is equal to 60 degree, we have a freewheeling duration for 30 degree here. Like that, 3 times in one cycle, right? So, for alpha 60, you can say that 3 into 30, 3 into 30 in one cycle. For example, if alpha is equal to 90 degree, if alpha is equal to 90 degree, in that case, how much time there is a freewheeling action here? Suppose if alpha is 90 degree, then it will start from 120, right? So 60 to that 120 will be freewheeling action, right? Like that, there is a 60 degree interval. Therefore, 3 into that 60 will give you the freewheeling action. Suppose if alpha is 120 degree, then what is the freewheeling duration? So T1 will start from alpha 90, 120 means T1 will start from 150. So this is 60 to that 150 will be freewheeling action. Okay, will be freewheeling action. So like that 3 times. Therefore, when alpha is greater than 30 degree, how to generalize that freewheeling action? So we can say that alpha minus this 30 degree. Okay, alpha minus 30 degree. For example, alpha is 60. So alpha minus 30 means how much? 60 minus 30 will give you this 30 degree interval. Similarly, if alpha is 90, 90 minus 30 will give you 60 degree interval. Therefore, generalization we can write it like this: 3 into alpha minus pi by 6. This is when alpha is greater than 30 degree. This is when alpha is greater than 30 degree. In this way, we can conclude the freewheeling action. So, with this, we discussed that for 3-phase half-wave phase controlled rectifier, when the load is resistive, continuous and discontinuous conductions, and when the load is current stiff, always continuous conduction. Next, current stiff load with the freewheeling diode. Freewheeling action is there and freewheeling action is not there. Okay, we discussed all the possibilities. Now, let us look into equations. Now, let us look into the equations and let us start with resistive load. Now, if you look into the previous waveforms, we had a conclusion of when alpha is less than 30 degree, in case of resistive load, the nature of the conduction is continuous conduction. Okay, the nature of the conduction is a continuous conduction. So you just refer the previous discussion. Output voltage waveform was what are the numbers 1 and 2. You just take waveform number 2, that is a generalized waveform. So in that case, what are the limits? Follow carefully. First, let us find average output voltage. 1 by periodicity. 2 pi by 3 is periodicity. What are the limits for the waveform? Pi by 6 plus alpha to 5 pi by 6 plus alpha. And equation is blue color sinusoidal. 3 VMP sin omega t d omega t. Now, let us simplify this one. Take VMP outside. Therefore, we can write 3 VMP by 2 pi. Integration for sin omega t is minus cos omega t. Limits from pi by 6 plus alpha to 5 pi by 6 plus alpha. Okay. Now, 3 VMP divided by 2 pi. Now, substitute the limits. Upper limit minus cos of 5 pi by 6 plus alpha. Lower limit minus of minus plus cos of pi by 6 plus alpha. Okay. So what I will do here first, let us simplify these trigonometric terms. So 3 VMP divided by 2 pi. Now what I will do here, let us expand this cos of a plus b term minus cos 5 pi by 6 cos alpha minus of minus, that is plus sin 5 pi by 6 sin 5 pi by 6 cos alpha. Okay, sin 5 pi by 6, I am sorry, this is a cos a plus b, so it will be sin alpha, right? Next term, let us expand, plus cos pi by 6 cos alpha minus sin pi by 6 sin alpha. We know that sin 5 pi by 6 and sin pi by 6 both are equal, hence we can eliminate them. Now cos 5 pi by 6, cos 150 minus root 3 by 2. Therefore this term is minus of minus plus root 3 by 2 cos alpha plus cos pi by 6 is root 3 by 2 cos alpha. Therefore from this what is the simplification we will get? 3 root 3 by 2 pi VMP into cos alpha. 3 root 3 by 2 pi VMP into cos alpha. Okay, this is the expression for average output voltage. Now average output current I naught is equal to V naught by R. Average output voltage I naught is equal to V naught by R. Now in the previous lecture we discussed that whenever we are dealing with the resistive load, you have to calculate RMS value. Therefore let us find VOR square 1 by 2 pi by 3 integration limits pi by 6 plus alpha to 5 pi by 6 plus alpha square of the function VMP square sin square omega t d omega t. Therefore it will give you 3 VMP square divided by 2 pi integration from pi by 6 to pi by 6 plus alpha to 5 pi by 6 plus alpha sin square omega t can be expressed as 1 minus cos 2 omega t divided by 2. Next 3 VMP square divided by 4 pi integration for 1 is omega t. For cos 2 omega t integration sin 2 omega t divided by 2 limits pi by 6 plus alpha to 5 pi by 6 plus alpha. Next step 3 VMP square divided by 4 pi upper limit minus lower limit 150 minus 30 that is 120 can be written as 2 pi by 3 minus half into open a bracket sin of 2 into 5 pi by 6 that is sin of 5 pi by 3 plus 2 alpha is the upper limit minus sin of pi by 3 plus 2 alpha. Sin of pi by 3 plus 2 alpha. Now let us simplify these trigonometric terms separately in order to avoid a confusion. I would like to expand sin of a plus b term sin 5 pi by 3 cos 2 alpha plus cos 5 pi by 3 sin 2 alpha, that is the first term expansion. Now the second term expansion sin pi by 3 cos 2 alpha plus cos pi by 3 sin 2 alpha. Okay, we have to subtract this. So on this subtraction we can say these two terms will get cancelled out. Okay, cos 300 minus cos 60. Now sin 50, this is a 300, sin 300 is minus root 3 by 2. Sin 60, this is a root 3 by 2. Therefore here we will get minus root 3 cos 2 alpha. Minus root 3 cos 2 alpha. Let us substitute that here. So we want RMS voltage. What you have to do? You need to take a root for this completely. So VMP square will come out as VMP. Start a bracket. 3 by 4 pi, if you pull inside the bracket, then what will be? 3 and 3 will cancel out. 2 pi by 4 pi will give you 1 by 2. Minus into minus plus 3 into root 3, 3 root 3 divided by 4 pi into 2, 8 pi multiplied with cos 2 alpha under root. This is the expression for RMS voltage for a resistive load when alpha is less than 30 degree. Next, for this resistive load when alpha is greater than 30 degree, we had a conclusion of discontinuous conduction. We had a conclusion of discontinuous conduction. Now let us look into average and RMS values for this particular topic. So average output voltage V0 is equal to 1 by periodicity, that is 2 pi by 3. Now which waveform you should refer? Waveform number 4. If you look into waveform number 4, you will find the limits are pi by 6 plus alpha to pi VMP sin omega t d omega t. So we can further simplify this equation as 3 VMP divided by 2 pi integration for sin omega t is minus cos omega t limits from pi by 6 plus alpha to pi. Okay. Now this can be further simplified as 3 VMP by 2 pi. Now upper limit minus cos pi is equal to 1 minus of minus plus cos of pi by 6 plus alpha. Okay. So this will give you the expression for average output voltage under discontinuous conduction. Now follow carefully. When the load is resistive, for average output voltage equation there are two formulas. So you should not jump onto the formula directly. Okay, you should make sure that whether the given condition is continuous conduction or discontinuous conduction. Next, average output current is equal to V0 by R. Power delivered to the load is VOR square divided by R. Therefore, we have to calculate RMS voltage. Okay, we have to calculate RMS voltage. So how can we express that? VOR square is equal to 1 by periodicity 2 pi by 3 limits from pi by 6 plus alpha to pi square of the function VMP square sin square omega t d omega t. Next, now let us simplify this. 3 VMP square divided by 2 pi integration from pi by 6 plus alpha to pi sin square omega t can be expressed as 1 minus cos 2 omega t divided by 2. Integration is with respect to x-axis. Next, 3 VMP square divided by 4 pi integration for 1 is omega t minus sine 2 omega t divided by 2. The limits are pi by 6 plus alpha to pi. Next, 3 Vmp square divided by 4 pi, upper limit minus lower limit. Okay, what you will get? Pi minus pi by 6. I will get it as 5 pi by 6 minus alpha, second term, minus 1 by 2 into, now substitute upper limit, sine 2 pi, that is 0. Lower limit, minus of minus, make it plus, sine of pi by 3 plus 2 alpha, okay, plus 2 alpha. So this is a VOR square. For VOR calculation, what we need to do? You can take a root of this completely. Then this will give you the expression for RMS voltage. The expression for RMS voltage. Okay. These are the different calculations for a resistive load. Now there is one special case in this resistive load. Let us see that. Special case in resistive load. Now when alpha was less than 30 degree, average output voltage equation, what was the formula we got? 3 root 3 divided by 2 pi Vmp into cos alpha, okay, into cos alpha. Next, when alpha is greater than 30 degree, when alpha is greater than 30 degree, we had an expression 3 Vmp divided by 2 pi into 1 plus cos of alpha plus pi by 6, right? So we concluded earlier this equation is applicable for continuous conduction and this equation is applicable for discontinuous conduction, right? This equation is applicable for discontinuous conduction. Now I have a question of, if alpha is equal to 30 degree, which formula I should use? In fact, I have not defined any limits in the waveform also. If you observe closely, for waveform number 3, we have not yet defined any limits. We will see the reason. Suppose you can use any one formula. Substitute alpha is equal to 30 degree. Okay. So this is root 3 by 2. Root 3 by 2 into 3 root 3 by 2 pi into Vmp. You will get the same value if you use this formula also. That means for alpha is equal to 30 degree, in both cases you will get the same value. No need to worry about for alpha is equal to 30 degree, that is a specific case. Next one. So in phase controlled rectifier circuits, in single phase we discussed, if alpha is equal to 0 degree, if alpha is equal to 0 degree, then V0 is maximum, isn't it? Same conclusion is applicable for single phase also. Therefore, what is VO max? Alpha is equal to 0 means it comes under less than 30 degree category. Therefore, we will get VO max equation as 3 root 3 by 2 pi into Vmp. Cos alpha is 1 because cos 0 is 1. So, now observe carefully. If alpha is in between 0 to 30 degree, if alpha is in between 0 to 30 degree, very important case. Corresponding to 0, we will get output voltage VO max, and corresponding to 30-degree output voltage is, now you can take this one, root 3 by 2 times of 3 root 3 by 2 pi into Vmp, where that value is nothing but VO max. That value is nothing but VO max. Next, if alpha is increased beyond 30 degree, if alpha is increased beyond 30 degree, now just have a look at the waveform once. When alpha is increased beyond 30 degree, you just need to refer waveform number 4, that is just similar to waveform number 6 only. So when alpha is increased beyond 30 degree, just imagine this waveform size got reduces, right? What do you mean by that? Area under the waveform reduces. Therefore, when alpha is greater than 30 degree, our output voltage will be less than root 3 by 2 times of VO max, where root 3 by 2 is nothing but 0.866. How can we use these formulas while solving numerical problems? Now I will tell you, anyhow in the next video we will do problems. If output voltage is less than, or it is required to get output voltage 50% of maximum possible value. 50% means what? Output voltage is less than 86.6% of VO max. It comes under discontinuous conduction category. In that case, you should use this formula. Formula selection is very, very important. In both cases, you will get some firing angle, but you will end up with the wrong answer. So it is required to get 90% of maximum possible output voltage. It comes under first category. In that case, you have to select alpha less than 30 degree formula. That is this first one. Okay. So in order to address this concept, we will take some numerical examples, right? So these are various cases for resistive load. Next, let us look into equations for current stiff load. What do you mean by current stiff load? An inductive load with constant load current. So if you look into the waveforms, what are the waveforms for this particular case? Waveform number 1, 2, 3 and 5, right? So for all these waveforms, integration limits are same. Therefore, our average output voltage equation will be same. So what we can say here, for any firing angle, average output voltage V0 is equal to 1 by periodicity, 1 by 2 pi by 3. Integration limits pi by 6 plus alpha to 5 pi by 6 plus alpha. Vmp sin omega t d omega t. Okay. Vmp sin omega t d omega t. Now 3 Vmp divided by 2 pi, integration for sin omega t is minus cos omega t, limits pi by 6 plus alpha to 5 pi by 6 plus alpha. In fact, we derived this equation earlier. Instead of repeating, let me write down the conclusion directly. So this will give you 3 root 3 by 2 pi Vmp into cos alpha. Okay. Now for this current stiff load, no need to go for RMS calculation, and hence power delivered to the load can be simply written as V0 multiplied with I0. That's all. Okay. So this is the only equation for current stiff load, right? Next, what is the next scenario? Current stiff load with the freewheeling diode. Current stiff load with freewheeling diode. Okay. So in this particular case, when alpha less than 30 degree. When alpha less than 30 degree. Waveform equations. V naught is equal to 1 by 2 pi by 3 integral pi by 6 plus alpha to 5 pi by 6 plus alpha. VMP sin omega t d omega t. This integration is just the same as earlier, and hence we can write V naught is equal to 3 root 3 by 2 pi VMP into cos alpha, okay, into cos alpha, right? And because of current stiff load, P naught is equal to V naught multiplied with I naught, that's all. Now, when alpha is greater than 30 degree, when alpha is greater than 30 degree, we can write V naught is equal to 1 by periodicity integration from pi by 6 plus alpha to pi VMP sin omega t d omega t. Earlier we derived this equation. What was the conclusion? 3 VMP by 2 pi. Now notice here, root 3 was not there. Don't mug up with the root 3. 3 VMP by 2 pi into 1 plus cos of pi by 6 plus alpha. 1 plus cos of pi by 6 plus alpha. And I naught is equal to V naught by R. These are all the different equations for 3-phase half-wave phase controlled rectifier. We will take up numerical problems in the next video. With this, I will conclude this lecture. Thank you.